And then the last one is linear, right? What am I adding each time? 4. So that's my slope. So my slope is 4. Okay, so y equals mx plus, what's my starting value? What's my y-intercept? 2. Now look, I said in the previous page that if a is positive, or if a is bigger than 1, it's a growth factor. And if a is stuck between 0 and 1, it's called a decay factor. So this is a decay factor. Now look what's happening to my values as x gets bigger. They're shrinking. They're getting smaller. If a is bigger than 1, we have a growth factor. So look at this table. What's happening as x gets bigger? What's happening to my y values? They're growing. They're getting bigger. That's why these are called growth factors, because your outputs are getting bigger as I always consider x as time continues on. So decay, growth, growth. Make sense? Good. All right, so let's look at the graphs of these. I'm going to put the table of values up that we made. So here's our table of values. This is not the best of screens because we're going to run out of room as soon as we hit 4. We'll have to maybe make 16 go up high. But let's just start plotting some of these points. Okay, so over 1 up 2, over 2 up 4, over 3 up 8, over 4 way up high at 16, so 10, 11, 12, 13, 14. Boy, it's like right at the top of the page. And then I'm completely out of room when you hit number 5, when you hit 5, 32. So let's look at some values that are a little bit lower. So if my input's 0, what is 2 to the 0? What's anything to the 0 power? 1. Try on your calculator, put in a half. And put in, let's even go lower. How about, no, let's not do a half. Let's do -1. And then -2. Let's see what kind of values we get out for -1 and -2. So 2 to the -1. You guys get a half? 2 to the -2.
You got your calculator just a little off.
Oh, yeah, there you go. Thank you. 2 to the -3. So you can see these values are getting smaller and smaller. They're not going to hit 0. They're just going to keep getting smaller and smaller. All right, so let's plot a couple of these points, and then we'll look at the graph on our calculator. So let's look to see what the graph looks like. What's your graph, increasing or decreasing? You go from left to right.
Increasing?
So, yeah, increasing. Looks something like that, doesn't it? Something like that? All right, so this is an increasing function, and it should be, because 2 is going to be a growth factor. All right, I'm going to plot this on Jake's calculator, and then we're going to look at it on this. Looks somewhat similar. If we do it in Zoom 6, same kind of concept, yeah? What can you tell me about an x-intercept? There isn't one. There isn't an x-intercept, but there definitely is a y-intercept. What's the y-intercept? 0, comma what? 1. What can you tell me about the domain from left to right? Is there a number that I cannot raise to a power of 2? I can do positives, I can take 2 to the negatives, and I can take 2 to the 0. So the domain is all reals. What kind of numbers am I getting out? What quadrants is that graph stuck in? What quadrants? It's stuck in quadrants 1 and quadrant 2, right? There aren't negative values for exponentials, for basic old c to the times a to the x. So the range, because there's not an x-intercept, I'll write it this way to start, it's just all positive. Oh, not zero. It's just all positives. The range are all positive reals. Or an interval notation from 0 to infinity. However you want to word it, it's just positives. Yeah, now let's look at it. Now horizontal asymptotes, we said that that's like the runway, right? Where the plane gets closer and closer but never touches. These are unusual because there's only a runway in one direction, right? So the horizontal asymptote is technically y equals 0, but I'm going to show you some limit notation. So this is good. This is going to kind of get you ready for pre-calc. You ready? Let's see if this makes sense. So the limit of this function as x goes towards infinity. So as x gets super, super big, what does this function do? It gets really big or really small? Really big. Okay. But let's look at the limit of this function as x goes towards negative infinity. So as x goes off to the left, what's happening to this function? It's leveling off to what? 0. And that's really the best way to denote that there's a horizontal asymptote, because it only has this asymptote on its left end. The right end, it explodes, right? It's huge, like super fast. It's the fastest growing functions are these exponentials. But on the left, it just levels off to 0. It's very boring. It just kind of hugs that x-axis. And that's what's called limit notation. And that's really the only way to let the viewer know, like in mappy terms, that on the right-hand side, the behavior explodes, and on the left-hand side, it just hugs 0. Does everyone see it? Like now that they kind of look at it, so it makes a little bit of sense. Limit notation, it's all good. All right, is there a vertical asymptote? No. No vertical asymptote. Okay. And I thought I would just talk about smooth and continuous because I was doing that in my pre-calc class. So you guys can handle that. A graph that is smooth has no jagged corners in it. So this is a nice smooth graph. A graph that is not considered smooth, I'll graph it for you, and I know you've seen it. This is a graph that is not smooth. That absolute value has a corner in it. Do you see it? It's the V. That is not considered a smooth graph. But this is a smooth graph. There's no corners in it. No corners. And it's continuous because there's no break in it. Right? Can't you draw the whole graph without picking up your pencil? Yes. So it is also continuous. Is this a one-to-one function? Does it pass the horizontal line test? Yes, it does. So what does that mean then? It has a what?
One output for one input?
For every output, there's just one and only one input, right? So because of that, we know it has an inverse. And the inverse function is what we're going to talk about on Friday, and it's a logarithm. So its special partner is a logarithmic function of the same base. All right, so what did we say the base to this exponential function is? It's y equals 2 to the x. So what is its base? 2. Why do you think it's called a growth factor? Look at the graph. If you go from left to right, what's happening to it? It's increasing, like super fast. It's called a growth factor because the graph is increasing. And I'll pick that up in a minute. The graph is increasing. Oh, if I can get that up there. What do you think? Does that make sense? I mean, that's everything you need to know about an exponential. Horizontal, vertical, x-intercept, y-intercept, increasing, decreasing, domain, and range. We got it all in. So let's do it now for, I think I have 1/2 to the x. We'll talk about what that 4 does, but we already know what the 4 does. All right, so I'm going to make a table of values on Jake's calculator. And you don't have to do this. I'm just going to pop the table up. So he has this nice scrolling. So we'll start at -2 because we can get that on my graph. Okay, so x, y. So when x is -2, y is 16. And we'll talk about that. We'll try to figure out why that's true. When x is -1, y is 8. 0, 4. 1, 2, 2, 1, 3.5. Well, these y values, as x gets bigger, are shrinking. Do you see that? They're getting much smaller. So let's plot these and figure out what's going on with that. Okay, -2. I'm way down here at 16. 10, 11, oh, no, I'm up here. 216. That was very close to the top of the page, right? 11, 12, 13, 14, 15, somewhere like 16. And then -1 up 8. 0 up 4. Well, that makes sense, right? Because my starting value should be at 4. Over 1 up 2. Over 2 up 1. Oh, that starts to shrink. 3 at 1/2. I'm going to put 4 in there just so you can see. 4 is 0.25. You guys get something look like this? It's hugging that. Something that looks something close like that.
So how do you make a rough graph?
I just plotted these points.
Oh, back to the question earlier, smooth versus rough.
Oh, if it's smooth, it means there's no corner. So like an absolute value or these piecewise functions that you do in pre-calc.
Oh.
If it's a corner, it's not smooth.
Okay.
Yeah. Has a corner. How do you spell corner? Is it O-R or E-R? E-R? Okay. Corner. Then it's not smooth. Yeah. Okay, you ready? X-intercept. None. Y-intercept. 0, 4. Increasing or decreasing? Decreasing. Decreasing. Domain. Free points. All reals.
Wait, quick question. Is it going to always be all real?
Yep. Range. All positive reals. All positive reals. Y is greater than 0. 0 to infinity. Right? However you want to think about it. Does it have a horizontal asymptote?
Yes.
Yes. What end behavior? On the left or on the right?
Right.
On the right. So yes, it does have one, but I'm telling you, when you get into pre-calc next semester, if you decide to take 1411 or 1413, they're going to make you be very specific. So I'm just going to show you what it looks like. So they're going to say the limit of my function as x goes off to infinity, as x gets really, 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 really big, the y value is kind of boring. It just goes to 0. What's happening to this function as x gets super, super small? Look at your graph. What's happening? As we go off to the left, what's your function doing? It's huge. Yeah, it's going off to infinity. Super big. That's like just such a much better way to denote that. Just to let the viewer know it's only a right end behavior. So is this smooth and continuous?
Mm-hmm.
Yes, it is. Is it one-to-one?
Yes.
Yes, it is. So it will have an inverse.
Yes.
Will have an inverse. And that's what we get to do on Friday. What is the base of this exponential function? 4. Yeah, it's whatever you're multiplying by. So 4 is the starting value and the 1/2 is your base. It's called the decay factor. Why do you think it's called a decay? What's happening as my function goes from left to right? What's happening? It's decreasing. It's getting smaller. So it's called a decay factor because my function is decreasing. Right? Have you guys ever done or heard of radioactive carbon dating, right?
Yeah.
That's an exponential function, and we'll do a couple of those problems in here. It's just based on this exponential decay. So that function is an exponential function. All right, so let's just kind of review it. You ready? If C is positive, which is always going to be positive until we start messing a little bit, and A is greater than 1, then the function f is increasing. If A is bigger than 1, then your function is going to be rising, and it's an exponential growth function. The y-intercept will always be 0, comma c. C is that starting value. If A is some number stuck in between 0 and 1, like 1/2 or 1/4, the function is decreasing. It's an exponential, what do they call it in the book? Instead of growth, decay. Yep, it's a decay function. And again, the y-intercept is 0, comma c.
What's the term regress? Would that be appropriate?
Regress? I've never heard of it. I mean, when you,
Exponential regress?
oh, we're going to do exponential regression.
Is that?
Yeah, and we're going to do it on our calculator.
No,
We'll find
is that
models.
a separate term? Do I have those mixed up?
Probably not. I've just never heard of
Decay
it.
and regress.
I'll look it up. Maybe it might be.
Okay.
Yeah, is that what maybe in bio or in chemistry they've talked about exponential regress?
I took statistics,
I don't remember talking about it in stats, but it's a new book. Maybe the new author talks about it. I'll look. Did you use the Moore book? Do you remember?
so.
Oh, I'll look it up. I'll look. I'll ask Lori, or I'm not
I just
teaching.
want to know if I write down regress, if I'll get points off.
Well, I usually have you get to circle growth or
Oh,
decay.
okay,
So
that's
then you
fine.
won't have to worry about it.
Cool. I'm happy with that.
All right, we'll come back to this one. I want to get to this so that if you start your My Math Lab, it won't be confusing. So I just want to start this real quick, and we'll come back and do that. You ready? I am going to do this on my calculator. Now, this is right out of your textbook, and it's like, oh my God, what in the world are they talking about? So I'm going to put this into my calculator, and then we'll understand what they're talking about. So they want to know what this expression does as n gets wicked large. N goes off to infinity. Right? I'm going to put this in my calculator. But I'm going to use x because we don't have an n on here. All right. So I put that expression into my calculator. 1 plus 1 over x all to the x. Is that okay? And I'm going to change Jake's settings so I can physically make x get big. So let's look at x is 10. That's kind of big, but not really big. Let's make x 100. Let's make x even get bigger. Let's make x 1,000 or 10,000. Now we're talking. Now we're getting big. How about 100,000? Woo! Let's go to 1,000,000. We're really big now, right? If we're talking about millions. What's happening to those y values? Are they changing drastically as x gets super big? No, it's hardly changing at all. Let's make it not even changing, right? So this constant was uncovered, and I think it was Euler who uncovered it. And he did many, many iterations of this limit and said the y value is not changing. It's constantly this 2.718. And so this number is used so often, and we'll see where it's used, that he decided to call it E. And it's what's called the natural base. It's like pi. When I say pi, what do you think? 3.14. When I say E, now you're going to go 2.718. Just like pi is 3.14, but it keeps going on, right? E is the same concept. It's just this irrational number, but it came up so often that people just got to name it. So I think Euler got to name it this nice E. Look at Euler at Euclid. I'll look it up. Okay, you ready? It's on your calculator. So you guys know how to find pi on your calculator, right? Do you see pi right there above the little caret symbol? Do you guys see where E is on your calculator? You see where E is? Look at your division symbol. Do you see the blue E? Do you see it? Or yours might be in yellow. So it's just like pi on your calculator. There's E on your calculator, 2.718. And that's where it uncovered. It was just truly some mathematician was fooling around with these limits and uncovered this natural number. Just like how pi was uncovered, right? The Greeks kept taking the ratios of the diameters to the circumference, and they noticed every single time it was 3.14. So it's the same concept, just some mathematician uncovered it. So this E value is right above the division symbol. You can find it in different places, but if you look at your division symbol, you'll see an E on your calculator. And it's what's called the natural base. Now, if I'm looking at this, let me ask you this question. This function, is it going to be a growth function or a decay function if E is 2.718? It's going to be growth, right? So it's this natural base that's a growth, has this growth concept. It's a growth function. Last big concept. What time does this class end? I know I should know this, but I really don't. What time? Okay, we'll do 2 problems and we'll call it a day. I thought we'd get this done, but don't think we're gonna. All right, does this make sense to you? Are you just staring at that and going, okay, yeah, that just makes